On Friday, April 13th, 2029, a point of light will race across the night sky over parts of Europe, Africa, and Asia. It will look faint and harmless, almost like a satellite, but that light will be an asteroid roughly the length of a large cruise ship, moving so close to Earth that it passes inside the altitude used by geostationary satellites. Its name is Apophis. At closest approach, it will be only about 32,000 kilometers above Earth's surface. Smaller rocks have passed closer, but no known asteroid more than 300 meters wide is expected to come this close for the foreseeable future. There is a problem, though. It is not the problem that made Apophis famous. This asteroid will not hit Earth. The real problem is what this safe encounter reveals about all the dangerous objects we have not found, and how little we still know about what happens when gravity grabs a loose mountain of rock and starts to twist it. June 2004. Astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi were observing from Kitt Peak National Observatory in Arizona when they found a faint object moving against the stars. It received the temporary designation 2004 MN4, which sounded more like an inventory code than the name of a future global celebrity. The object was observed for only a short time before sunlight and orbital geometry made it difficult to follow. In asteroid tracking, that is a serious complication. A few observations can show that an object is moving, but they do not always reveal exactly where its long orbit will carry it years later. Imagine trying to predict where a thrown ball will land after seeing only the first fraction of its flight. A tiny error in speed or direction grows with distance. For months, the asteroid was effectively lost. Then it was recovered in December. New observations were added, its projected path narrowed, and the numbers became alarming. On Christmas Eve, calculations placed the chance of an Earth impact in 2029 at roughly 1 in 37. That was about 2.7%, the highest impact probability ever assigned to an asteroid of this scale. Apophis reached level 4 on the Torino Impact Hazard Scale, another record that no object has surpassed. The date made the story irresistible. Friday the 13th, 2029. A large asteroid on an apparent collision course with Earth. Within days, headlines were treating a changing probability estimate like a countdown. But probability is not prophecy. That 1 in 37 figure did not mean astronomers believed Apophis was probably going to hit. It meant the available observations left a long corridor of possible positions, and Earth happened to sit inside part of that corridor. The asteroid had one real path. Scientists simply did not know that path precisely enough yet. That distinction is easy to lose when the risk number rises. As more observations arrive, an impact probability can increase before it collapses. The uncertainty corridor shrinks, and if Earth remains inside it, a larger share of the remaining paths may cross the planet. Only when better measurements move the entire corridor away does the danger disappear. Astronomers searched older sky images and found Apophis, hiding in observations made before its official discovery. Those earlier positions extended the measured arc of its orbit. The 2029 collision scenario was eliminated. Relief did not end the story. Earth's gravity would bend the asteroid's path during the close pass, and early models raised another possibility. If Apophis crossed an extremely narrow region in space known as a gravitational keyhole, Earth's pull could place it on a later collision course. For a time, 2036 and 2068 remained dates of concern. The keyhole idea sounds exotic, but the physics is straightforward. A close flyby acts like a gravitational steering maneuver. Pass on one side of Earth at one precise distance, and the planet changes the asteroid's speed and direction by one amount. Move that path slightly, and the new orbit changes. A keyhole is the small patch of space that produces just the wrong change, sending the asteroid back to meet Earth years later. This is where patient measurement did what dramatic speculation could not. Optical telescopes watched Apophis over multiple returns. The giant Arecibo radio telescope in Puerto Rico transmitted radar signals toward it. NASA's Goldstone Solar System radar in California measured the returning echoes. Radar can determine distance and motion with extraordinary precision, turning a blurry dot into a much tighter orbit. By March of 2021, new radar observations had removed the remaining 2068 impact scenario. NASA concluded that Apophis poses no impact risk to Earth for at least the next 100 years. That sentence matters enough to say plainly. Apophis will safely miss Earth in 2029. It will not strike the planet, it will not hit the moon, and its path does not threaten the satellites in the crowded geostationary belt. The satellite claim needs a little explanation because the comparison is real. Geostationary satellites orbit about 35,800 kilometers above the equator. Apophis will come closer to the surface than that. However, the asteroid approaches on a steeply inclined path and does not sweep through the equatorial ring where those satellites cluster. It passes inside their altitude without charging through their neighborhood. The flyby remains astonishing. NASA describes it as the closest known approach by an asteroid larger than 300 meters for the foreseeable future. Estimates differ depending on how size and distance are counted, but an encounter in this class may happen only once every several thousand years. Recorded civilization may never have witnessed one, and no earlier generation had radar arrays, space telescopes, and spacecraft ready to watch. Apophis is not a perfect sphere. Radar observations suggest an elongated body, perhaps shaped like a peanut with two broad lobes. Its effective diameter is estimated at roughly 340 meters, while other measurements place it closer to 375. It tumbles through space rather than rotating neatly around one stable axis. Its surface probably resembles the stony material found in ordinary chondrite meteorites. Its interior is a bigger mystery. Like many small asteroids, Apophis may be a rubble-pile, a collection of rocks, dust, fractures, and empty spaces held together by weak gravity and contact forces. If you stood on it, escape speed would be so low that a hard jump could become a very bad career decision. That loose structure is why the safe flyby has become such an important experiment. Earth is about to do something to Apophis that scientists cannot reproduce at full scale in a laboratory. As the asteroid falls toward our planet, Earth's gravity pulls on the near side slightly harder than the far side. That difference creates tidal stress. The same basic effect raises ocean tides and slowly stretches worlds, but on a small, irregular rubble pile, it may rearrange the surface. Apophis will not cross Earth's Roche limit, so nobody expects it to be torn apart like Comet Shoemaker-Levy 9 was near Jupiter. The stress will be far weaker. Yet weak does not mean irrelevant when an asteroid's surface gravity is tiny and loose boulders may already sit near the angle where a small disturbance starts a slide. Computer models suggest several possibilities. The asteroid may experience brief, seismic shaking as Earth's tide changes rapidly across its body. Rocks could shift, slopes could fail, dust could lift and settle somewhere else. Material darkened by ages of radiation and micrometeorite impacts could move aside, exposing brighter rock beneath. Earth will also torque Apophis, changing its tumbling rotation. That altered spin may keep reshaping surface slopes long after the closest pass. Some areas could become steeper, others flatter, and slow landslides might continue as the asteroid settles into its new motion. Or the visible changes could be subtle. This is not a guaranteed spectacle of boulders flying into space. Scientists do not yet know Apophis well enough to say how much movement will occur. That uncertainty is the scientific jackpot. A dramatic change reveals weakness and mobility. A quiet passage places limits on how strong and stable the asteroid must be. The same data could solve a broader mystery. Some near-Earth asteroids look unexpectedly fresh, as if their weathered surfaces have been renewed. Close planetary encounters may be responsible. If cameras detect new bright patches or shifted rocks on Apophis after 2029, Earth may have caught an asteroid resurfacing in real time. The planet will also rewrite Apophis's solar orbit. Before the encounter, Apophis belongs to the Aten group, asteroids whose average distance from the Sun is smaller than Earth's. After Earth's gravitational swing, it will move into the Apollo group, following a larger orbit that takes longer to complete. Its orbital period is expected to change from about 324 days to roughly 423 days. Earth will have redirected a multi-million-ton asteroid without touching it, simply by being there. That is an impressive prediction. But researchers want more than a before and after orbit. They want to watch the moment of change, and that creates the first practical problem. NASA's OSIRIS-APEX spacecraft is already on its way. It is the same spacecraft that collected a sample from asteroid Bennu under its former name, OSIRIS-REx. After dropping the Bennu capsule over Earth in September of 2023, the spacecraft fired its engines and began a new mission to Apophis. OSIRIS-APEX can begin observing the asteroid as a distant point before the flyby, and it can watch from tens of thousands of kilometers away during the encounter. Orbital mechanics prevent it from arriving for close, detailed inspection beforehand. Its main proximity operations begin after Earth has already performed the experiment. That makes OSIRIS-APEX an expert investigator arriving at a scene moments after the event. It can map the new surface, search for fresh exposures, measure the altered spin, and compare those results with earlier radar and telescope data. It can even descend close to the surface and use its thrusters to disturb dust, revealing how loosely the material is packed. But a post-encounter investigation cannot recover every detail of what happened during the closest minutes. If scientists want a true before and after comparison at spacecraft resolution, another mission has to arrive first. Europe's answer is Ramses, the rapid Apophis mission for space safety. The European Space Agency plans to launch it in 2028 and rendezvous with Apophis about 2 months before the flyby. Ramses is designed to stay with the asteroid through the encounter, recording its shape, motion, and surface as Earth's gravity takes hold. The schedule is unforgiving. Space missions usually take years of design, testing, and cautious review. Apophis will not delay its appointment because a component arrived late. In February of 2026, the European Space Agency signed a major spacecraft development contract, pushing Ramses into construction, assembly, and testing. The mission must be ready for a launch window that does not move. Ramses is expected to carry small companion spacecraft as well. One planned CubeSat, named Don Quixote, is intended to operate on the asteroid's surface. A sensor riding directly on Apophis could feel shaking that an orbiting camera might only infer from moving dust and rocks. Together, Ramses and OSIRIS-APEX could provide the closest thing planetary science has ever had to cameras on both sides of a natural asteroid stress test. Ground observatories will add another layer. Goldstone radar is preparing to image Apophis at resolutions of a few meters, placing tens of thousands of radar pixels across the body. Optical telescopes around the world will measure brightness, color, position, and rotation. All of that coordination is also a rehearsal. If a dangerous asteroid were discovered tomorrow, observatories would need to share measurements. Governments would need to communicate risk. Engineers would need to build or redirect spacecraft, and scientists would have to decide whether touching the object would make the situation better or worse. That last question sounds uncomfortable because it is. A spacecraft can exchange momentum with an asteroid. Usually the effect is tiny, but planetary defense lives in the world of tiny changes accumulating over years. A NASA study team examined whether intentional or accidental spacecraft contact with Apophis could push it toward a future gravitational keyhole. The team confirmed that the asteroid is safe on its natural path and evaluated mission profiles so that scientific exploration does not create a new hazard. The scenario is unlikely, but responsible planetary defense requires more than saying unlikely and moving on. It requires calculating how unlikely, then designing the mission around the answer. There's another concern. Multiple missions, impactors, landers, or close operations could contaminate the experiment scientists came to observe. If a rock moves, was it Earth's tide or a thruster plume? If the spin changes slightly, was it gravity or contact with hardware? International coordination matters because Apophis is both a scientific target and a potentially hazardous asteroid, even though its current trajectory is safe. If you enjoy documentaries that separate real space risks from viral panic, subscribe. The next asteroid headline will arrive with a probability, a date, and plenty of noise, and knowing how those numbers work changes the entire story. The larger problem begins with a number that receives far less attention than Apophis. Astronomers estimate that roughly 25,000 near-Earth objects at least 140 meters wide exist. Objects in that class can cause regional devastation. According to NASA, less than half have been found. That means the catalog is not a complete map of the threat. The fact that no known large asteroid has a significant chance of hitting Earth in the next century is reassuring, but the word known is doing a lot of work. Apophis was discovered 25 years before its close approach, giving scientists decades to refine its orbit. Other objects have offered almost no warning. Asteroid 2019 OK, estimated at roughly 60 to 130 meters, was discovered on the same day it passed inside the Moon's orbit. Asteroid 2020 LD, potentially as large as 200 meters, was found only after its close pass. The blind spot is partly geometric. Ground telescopes work best at night, looking away from the sun. An asteroid approaching from the daytime sky can remain hidden in glare until it is nearly here. Weather, moonlight, location, and an object's dark surface can make detection harder. The smaller the asteroid, the fainter it usually appears. Yet small does not mean harmless. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 20 meters across. Its airburst shattered windows across a wide area and injured around 1,500 people, mostly through flying glass. An object several times larger could do far more. Apophis is therefore the ideal public demonstration and the wrong object to panic about. We know where it is. We know when it will arrive. Radar has narrowed its 2029 trajectory to within a few kilometers. The dangerous asteroid is the one still hiding in the data, the glare, or the part of the sky our surveys have not covered deeply enough. New systems are being built to close that gap. The Virasi-Rubin Observatory can scan huge areas of sky repeatedly, detecting faint objects that move or change. NASA's planned NEO Surveyor Space Telescope will use infrared light, which is valuable because dark asteroids still radiate heat. From space, it can search regions closer to the sun's direction than many ground observatories can manage. Detection is only the first half of planetary defense. Once an object is found, scientists must determine its orbit, size, shape, rotation, composition, and internal structure. Those details decide what kind of response could work. NASA's DART mission proved that a spacecraft can alter an asteroid's motion. In September of 2022, DART struck Dimorphos, the small moon of asteroid Didymos, and shortened its orbit around the larger body by more than half an hour. Humanity deliberately changed the path of a celestial object for the first time. The result was encouraging, but it also exposed the importance of structure. DART blasted out a huge cloud of debris. The recoil from that ejecta added momentum and increased the deflection. A solid metal body, a fractured rock, and a porous rubble pile would not all respond the same way to an identical impact. That is why Apophis matters beyond the beautiful radar images and the naked eye event. Earth will apply a known gravitational force to a suspected rubble pile. Ramses, OSIRIS-APEX, Goldstone, and observatories across the world will measure the response. Those measurements can improve models used for an asteroid that actually is on a collision course. Warning time remains the decisive advantage. With decades available, a tiny velocity change can grow into a miss of thousands of kilometers. With only days available, there may be no realistic deflection mission at all. Planetary defense is less like firing a missile at the last second and more like nudging a train onto a different track before it reaches the junction. This is also why sensational claims about secret impact risks are so damaging. They focus attention on an asteroid that has been measured exceptionally well while obscuring the quieter work that actually reduces danger. Telescopes, follow-up observations, radar time, infrared surveys, shared databases, and international planning do not look cinematic. They are the reason Apophis changed from a Christmas Eve scare into a scientific opportunity. On the evening of April 13th, 2029, viewers under clear, dark skies should not expect a fireball. Apophis will remain far outside the atmosphere. It should appear as a star-like point moving steadily against the background sky, crossing a noticeable distance in only a few minutes. For observers in favorable parts of Europe, Africa, and Asia, no telescope may be necessary at peak brightness. Other regions will need binoculars, a telescope, or an online broadcast. Exact local visibility will depend on location, darkness, weather, and updated predictions closer to the date. Above the atmosphere, radar beams and spacecraft cameras will be watching something more subtle than a near miss. They will watch Earth's gravity take an asteroid that once terrified the world and turn it into a different object, with a new orbit, a changed rotation, and perhaps a freshly rearranged surface. The strange part is that Apophis itself may teach us how to deal with a future threat. Its original risk forced astronomers to improve the orbit. Its safe passage is forcing agencies to practice international observation. Its unknown interior is giving researchers a natural test of rubble-pile physics. Even the rush to reach it before the deadline resembles the time pressure of a real defense mission. That turns the opening image on its head. The point of light passing below geostationary altitude is not the danger. It is the warning shot that misses on purpose, giving humanity a rare chance to examine the weapon before another one arrives. Apophis will pass safely. Earth will barely notice. The asteroid may shake, tumble, and leave on a new path around the sun. What matters after that is whether we use the encounter to find the objects still hidden, understand what they are made of, and prepare before one of them appears with a date that cannot be cleared by better measurements.